Marine litter is high on the scientific and political agendas and of major concern for European citizens. More than 80% of marine litter is plastic. It is estimated that by 2050, more plastic could be in the ocean than fish. It can be found on beaches, mostly produced locally, on the ocean surface, in animals, and on the seafloor. Microplastics can get into the food chain together with the integrated and absorbed toxins. As a component of marine litter, the presence and accumulation of plastic debris in the marine environment has been recognized as a major environmental problem due to its implications for marine ecosystems and services to humans. IUCN estimates that 12 billion tons of plastic are leaking into the global ocean every year, causing an unprecedented environmental crisis, whereas global annual production of plastics increased 20-fold in the last 50 years, exceeding 415 million tons per year, thus becoming eventually the main source of microplastics. In addition to possible health risks, the damage to marine ecosystems and the blue economy, tourism, and other maritime sectors due to plastic litter are enormous. Clearly, marine litter pollution is a complex and multidimensional environmental issue that involves human activities, industry, urban waste, tourism, maritime traffic, being its main source, as well as physical processes like ocean currents, waves, wind, that controls the fate of litter in the marine environment. Its mitigation requires knowledge on sources and fate of marine litter, as well as the development of cost-efficient methods and policies for its reduction. CLAIM contributes to the effort of the international community to advance our knowledge on the current status of marine plastic pollution and provides innovative technologies to reduce the amount and impact of plastic pollution in the Mediterranean and the Baltic Seas. It is a joint effort of 19 partners from across 13 European countries, Tunisia and Lebanon, and is led by HCMR. CLAIM's overarching objectives are to advance our knowledge on the current status of marine plastic pollution, provide innovative technologies able to reduce the amount and impact of plastic pollution on the ecosystem-based services of the Mediterranean and Baltic Seas, set the basis for operational forecasting of the impacts of marine plastic litter pollution on ecosystem services, and provide advice for management decision-making, including fostering social acceptance and assessment of economic impacts. Existing practices for cleaning plastic litter in the sea mainly target on macroplastics with the use of these in the establishment of a circular economy, yet still in its infancy. Microplastics represent a major threat for marine ecosystems and their services, with no robust methods for their treatment with existing technologies. To reduce the introduction and abundance of macro and microplastics in the marine environment, CLAIM develops and demonstrates innovative technologies and approaches suitable for removing macro and microplastic litter at their point of introduction to the marine environment, that is, rivers runoff and wastewater treatment plants, and in the marine environment. Furthermore, CLAIMs develop and demonstrates fit-for-purpose modeling tools able to identify the regions and services like fish stocks, aquaculture, sensitive habitats, and biodiversity under increased threat from the introduction of plastics. The proposed approaches are characterized by low cost and small scale, having the potential to be adopted by ports, coastal authorities, every wastewater plant, and vessels, and thereby to tackle marine litter problem with a nearly as comprehensive, low-cost cleaning approach. Claims focus on small-scale and cost-effective solutions of little initial investment aims to make easier social acceptance and adoption. Furthermore, by defining approaches that focus on the major points of litter entry into the sea and technologies that allow its treatment, claim translates to the marine litter management the guiding principles of waste management, the waste hierarchy, prevention first, and the proximity principle, waste treated as close as possible to the point of arising. Existing practices on cleaning macroplastics include ocean booms for the exclusion of polluted sea areas, schema vessels for cleaning up the sea surface, vacuum trucks for coastal use, and finally manual collection of plastics. In the case of microplastics, there are no robust methods offering essential and integrated solutions. Plastic microbeads, fragments and fibers pass directly from household waste into wastewater systems and are too small to be retained by the standard filters used at sewage treatment plants. Therefore, to reduce existing quantities of microplastics in the marine environment, there is a need for innovative methods. For the wastewater treatment plants, a low-cost, automated and self-cleaning lab-scale filtering system for microplastic litter was designed and tested, placed prior to a photocatalytic nanocoating device in order to supply it with accumulated liquid litter, microplastics, of appropriate size to enhance the efficiency of the photocatalytic device by blocking the bigger particles that would need more time to be dissolved. An upscaled and redesigned model is installed and ready for field testing and demonstration in the wastewater treatment plant of Megara city in Greece. The claimed technological innovation aims to design and develop a photocatalytic device that will degrade microplastics in water under natural or artificial sunlight right after the prefiltering system, ensuring its optimum operation. Claim partners at KTH in Sweden fabricated a lab-scale prototype using green nanotechnology-based coatings that encourage polymer degradation. Metal oxide semiconductor nanostructures have been synthesized and chemically attached to supporting membranes to ensure photochemical activity without releasing the nanoparticles into the water stream. The efficiency of the lab-scale prototype was evaluated using polypropylene microplastics as test compound. The efficiency data showed that about 65% reduction in the volume of polypropylene microplastics can be obtained in about 21 days of irradiation. The proposed technology can easily be used in wastewater treatment plants where the effluent ends up into the sea and into rivers. It may also be used in potable water refineries, as numerous studies reported the presence of microplastics in treated tap and bottled water. It may be used in industries which use plastic for packaging, such as fresh cut production industries, plastic bottle production industries, plastic caps production industries, industrial laundry facilities. They could use this technology as a treatment stage of the wastewater treatment process. Also, these filters, 25 to 30 cubic meter per day water production, may be used in hotels or small complexes with wastewater treatment plants for 150 equivalent population. Nanotechnology has potential application in various sectors of wastewater treatment and management and is often more effective than conventional filters. Claim has developed an innovative floating boom, floating barrier, and marine litter collection and recovery system, the so-called Clean Truss Equipment Solution, to address the issue of marine litter. The Clean Truss system is an unparalleled and highly efficient solution to manually managing and removing marine litter from river and torrent mouths before the litter can enter into a larger body of water where the litter can cause negative effects on the marine environments and where plastics can break into smaller macro and microplastics, dramatically affecting marine life and marine ecosystems. The system has a highly efficient storage designed with multiple levels that can be remotely interchanged when filled. Systems are tailor-made for each installation environment and are intended to be designed in a range of shapes and sizes to meet the task at hand as efficiently and effectively as possible. The marine litter that will be collected from the clean trash system will be treated in specially designed pyrolyzer systems that have been developed in the CLEAN project, one for ports and marinas and one for vessels. Pyrolysis is the thermochemical decomposition of organic material at high temperature and in the absence of oxygen or in an atmosphere of inert gases. The process typically occurs at temperature above 430 Celsius degrees or 800 Fahrenheit and under pressure. It simultaneously involves the change of physical phase and chemical composition and is an irreversible process. Compared to combustion, pyrolysis has a lower process temperature and lower emissions of air pollutants such as PBDEs. Additionally, the scale of pyrolysis plants is more flexible than incineration plants. Nowadays, pyrolysis is getting attention for its flexibility to generate a combination of solid, liquid, and gaseous product in different proportions just by the variation of operating parameters such as temperature or heating rate. It also provides an opportunity of transforming materials of low energy density into biofuels of high energy density, at the same time recovering high-value chemicals. One of the great advantages of this process is that many types of raw materials can be used, including industrial and domestic residues. The scale model was built at NNL, which is New Naval's facilities in Lavrio, Greece, in late 2018, and a prototype was deployed at the river mouth of Kifissos River in Athens. The effectiveness and capabilities of the system passed all quality assurance testing, confirming that the system is ready to be installed in active long-term operational environments. It will continuously contain and remove marine litter from river mouths and be a commercial product purchased by authorities and all stakeholders related to the marine litter pollution. During the tests and after heavy rainfalls, the clean trash system collected in 10 days 8 cubic meters of marine litter composed mainly by plastics. Every installation of the clean trash system is tailor-made and strategically placed to operate with the highest efficiency and effectiveness while addressing the scale of the issue. System components are custom-built, designed to properly address the environment, location, and river of every installation. Operations follow a tested and structured format, with litter removal dependent on litter volumes in the river. This results in minimal operating costs and a reduction of the need for physical attendance by operators for long periods. The system can be continuously operated, monitored, and utilized to collect and compile a litter information database regarding the volume of litter exiting the river and the correlations of these volumes to weather and river fluctuations. Claims partner IRIS has developed a small-scale pyrolyzer, patented, for the treatment of solid waste with energy recovery. Using commercially available laser and arc welding technologies, IRIS generated a plasma for treating solid waste at very small scale. Plasma torches are only available at large scale. building an automated working prototype, a TRL-5, that treats small quantities of waste and obtains a combustible gas, syngas. Further development of the device, initially designed to be used by isolated communities like mountain villages, hamlets, allowed to carry a feasibility study for its application to treat the collected waste on board an autonomous vessel powered by wind and solar energy, which was awarded a Horizon 2020 SME Instrument Phase 1 grant, Project Sea Litter Critters. The study conducted that the solution, although feasible, might encounter low market interest from local authorities, but might be of interest for companies offering cleaning services to ports and tourist resorts. The goal of this innovation in the CLAIM project is to integrate small-scale thermal treatment devices, pyrolyzer, of small-sized vessels boards and in harbors. The solid plastic waste can be transformed into combustible gas that can be used immediately on site as an energy source for ships and lighting and heating in ports. This technology, suitable for marine litter that cannot be recycled due to contamination and multi-material composition, has been developed through the project Green Plasma, and it is further developed and tested within CLAIM, where IRIS has conceived, designed and patented with the use of thermal plasma technology a treatment that allows, due to the high temperature reached, up to 5,000 Celsius degrees, to transform any organic compound into gas, separating it from matrix. The system has great potential in circular economy applications, and it allows the recovery of raw materials and energy without harmful emissions and with minimal waste. The CLAIM project will facilitate better governance of the issue of marine litter by providing tools such as new models and concentration maps to give insights into the distribution of macroplastics greater than 5 millimeters and microplastics from 1 micrometer up to 5 millimeters, and scenarios to determine the efficiency of CLAIM's technologies. An ecosystem approach will guide the project through the evaluation of the potential benefit from the proposed litter cleaning methods to ecosystem services and human well-being. CLAIM's modeling tools monitor the fate and forecast the distribution of marine plastic litter pollution, both micro and macroplastics, in the Baltic and Mediterranean seas, with the aim to provide a better understanding of the impacts of human activities on ecosystem services. These tools will also evaluate the impact of CLAIM's cleaning methods in the marine environment. By identifying and mapping potentially threatened ecosystems, CLAIM will pay particular attention to the ecosystem services on which commercial fisheries and aquaculture rely. CLAIM's enhanced modeling tools include ocean circulation models, wave models, Eulerian tracer drift and sedimentation, and individual-based particle drift models. Historical data on visible and invisible plastic litter is collected from existing literature and databases from the Baltic and the Mediterranean seas. Spatial distribution of land sources of micro and macroplastics are mapped to provide realistic source inputs to the Eulerian tracer and Lagrangian particle models. For the Baltic region, CLAIM quantifies plastic litter in different categories, that is, microplastics due to tire wear and using personal care and cosmetic products that have never been part of modeling tools before. The ferry box is a system of integrated hydrological and biogeochemical sensors installed on ships of opportunity like ferries on fixed routes between Piraeus Heraklion in Greece, Tunis to Marseille, Tunis to Genoa, and Tallinn Helsinki that measure while the boat is underway. In these existing ferry box facilities, the claimed goal is to add an automated seawater sampling device and passive flow-through filtering system to assist the collection of data on the distribution of microplastics and understand their impact on marine ecosystems. The Ferrybox innovation has successfully passed a laboratory test on coastal waters and on board an RV vessel under point navigation. A prototype filtering system able to be configured with several diameters of filtering components and automated flow rate controllers has been designed, manufactured, and tested in a coastal sampling station and on board an RV vessel. The first test took place in the Seawater Sensing Laboratory at Millau Marseille on May 2019, aiming to simulate the use of the first prototype under controlled conditions and the retrieval of the stainless steel filters and collected materials. The flow rate, pressure control, overpressure conditions, and sampling collections were tested extensively using different configurations before installing the system in an RV vessel. A second testing experiment was performed on board the RV Salme during a scientific cruise on the Baltic Sea in May 2019, and the purpose was to evaluate the operational performance of the prototype system in realistic sampling conditions. The results of the testing procedures point out the necessary improvements to be made in order to install the second version of the system in the claimed ferry boxes to generate observations for model validation. In the Baltic Sea, a Eulerian tracer module is online embedded in the hydrodynamic ocean model to simulate transport of microplastics with including wave-induced transport, biofouling and sedimentation processes. The model grid size is 900 meters so that meso and sub-mesoscale eddies can be resolved. A Lagrangian individual-based model driven offline by the output of the high-resolution ocean wave models is implemented for modeling transport of visible plastics, macroplastics. A new approach for the resampling scheme is used, taking into account input sources in order to obtain a quasi-equilibrium spatial distribution. In the Mediterranean Sea, a basin-scale hydrodynamic model is online coupled with a Lagrangian individual-based model that is used to track the fate of floating plastics. Different sizes and types of plastics have been considered based on the dominant times found in the Mediterranean and also the size classes and available datasets that can be used for model validation. A yearly forecast of macroplastics pathways and concentrations is shown day by day, resulted by the so far collected data and models run. Thank you for attending us.